I'm going to talk about star formation and how the infall of gas and kinematics of this gas affects the star formation process. Stars form in molecular clouds, and it's through the motion of these gases that come together and in the very dense regions, when those blobs of gas, those clumps of gas, um, gather enough mass to form a star through gravity, that stars form. There are many other different physical processes that take place in a molecular cloud and in star formation. I will talk about some of them as we go along, but it's not just as simple as material coming in and forming a star. And that's why we need to study the kinematics of the gas in order to understand what's happening inside molecular clouds to see how stars form. And star formation is a multi-scale process. It involves processes that take place over a galactic scale, as seen here in this map of the CO, the more carbon monoxide emission in the millimeter of the molecular gas in a galaxy similar to our own. This is M51. Let's see. Do you see my third cursor? O no se ve el cursor. Sí, se ve el cursor. Okay. And you can see that it has spiral morphology similar to our own galaxy. And all this blobby things, these are different molecular cloud associations. If we zoom into those regions, we see molecular cloud complexes, and within those molecular cloud complexes, you see filamentary structure, and within those filamentary structures, you see clumps where a bunch of stars are going to form. And within those clumps, you see cores where 2 to 3 stars will form. And inside those cores, you see envelopes where the denser regions of the envelope, the denser parts of the core, where the stars are going to form. And the thing about probing those different scales is that you need to use different telescopes as well as different molecular lines to study the different densities and the different scales that entail the star formation process. Most of the stuff that I'll be talking about will be observing molecular line emissions from different molecules that are in molecular clouds. Molecular clouds, again, are the regions where stars form. And here's a cartoon of what a molecular cloud might look like. A molecular cloud will be about 10 parsecs in size, and here you have the conversion between parsecs and light years and kilometers. And within the low density region of a molecular cloud, we have regions that are denser, because clouds are inhomogeneous. They have regions of low density and regions of high density. So going into higher density, we have clumps, what we call clumps, and those are about 1 parsec in size. And those you can think of the clumps as the regions where the star clusters will form. Inside those clumps, we have even denser regions, the cores, where there are let's see if I have a tendency to go in the wrong direction. Sorry. Inside those cores, which are about 0.1 parsec in size, that's where one or a few stars will form. And each star will be surrounded by a disk. That's where eventually the planets will form. And the protostars will be powering what we call outflows, emanating from the poles, pushing the gas around it. And if we go into a little smaller scales, we then see the protostar surrounded by a disk. I won't be talking about that specifically, but I'll touch lightly on the disks in this talk. So you can see that from this picture, we're going from 10 parsecs to 0.1 parsec and even smaller. So more than 2 orders of magnitudes in range of scales. In addition to having a range of scales, we have a different structures that are a hierarchical structures that are identified in molecular clouds. And here's a cartoon of that hierarchical structure where you have the clouds, then the clumps, and inside the clumps you have filaments. And it is inside those filaments, those are elongated, dense structures inside clouds, where inside those filaments you'll see the cores where the stars and the disks will form. And so studying the structure and the kinematics of the gas at all different scales allows us to understand better the processes that take place in molecular clouds that allow the formation of stars and the impact that the stars themselves have on their surroundings. So that's what mostly I do with the observations that I take. So let's start with the filament scales. Here's a dust continuum map of a cloud in Orion B. This is near I believe the Horsehead Nebula is somewhere around here. Anyways, so this is dust emission. Okay, no, is it? Is it real? Yes, this is dust continuum emission. So molecular clouds are made of gas, molecular gas, and also dust. And even though the dust is about 1/100th of the mass of the gas, if you observed the dust continuum emission, you can see very clearly the structure of the cloud. However, you only see this in the denser parts. You are most likely to trace the denser parts of the cloud with the dust because you have to have a lot of dust in order to be able to see it clearly. And in real life, the filaments are not this pretty like here. This could be identified as a filament, and this could be identified as a filament. And inside those filaments, we have those cores, which are basically in dust continuum maps are seen as over densities, regions or blobs that have higher intensity than the background. Okay. So dust continuum emission, because dust emits, and we can detect that in the millimeter. Is great for understanding the structure of the cloud, but unfortunately, unlike the gas, you cannot study the kinematics of the environment because you don't have any information of that from the dust continuum emission. So instead, you have to observe the gas, the molecular gas, in the same region in order to understand the kinematics, how the gas moves around. And here I show the dust continuum map in grayscale. Is it in grayscale? Yes. And the contours are the dust continuum emission. And again, the dust continuum, as I said before, mostly traces the denser parts of the cloud. And the CO, the carbon monoxide, even though it is the most abundant, is the second most abundant molecule in molecular clouds. And so that's why we use it a lot to map the large scale structure of a cloud. But unfortunately, it's not very good at tracing the denser regions. And maybe you can see it here or not, but the dust continuum, which traces the denser parts of the cloud, doesn't seem to correlate very well with the grayscale map that comes from the CO, the gas emission. And this is mostly because the CO is optically thick. The CO emission is optically thick. You can only see up to a certain depth of the cloud with the CO. You're basically with the CO, you're only seeing the skin of the molecular cloud, and you cannot go through and map the denser parts. So we use a range of molecules in order to probe different depths inside a cloud. And as you go to the right in this figure, we're going to deeper and denser regions in the cloud. And you can see that, and this in astronomical parlance is you can think of it as extinction or just density. To go deeper and higher density regions, we use different molecules to trace those different layers inside the clouds. And as you would expect, the star formation, the gas that is deeply related to the star formation process would have to be dense. And so if we want to study what's happening to the gas that it's clearly associated with the star formation process, we would like to probe the denser regions. So here's an example of what you see with this different molecules, let's say. So again, going the wrong direction. So here's a small cloud, the B5 molecular cloud. Here's a map of the 13CO. It's a isotopologue of CO, which traces slightly higher density than the CO. This is B5. And yeah, you can see the structure of the general structure of the cloud. But if you concentrate on this region around this protostar, and you take a look at the continuum emission from the from dust, you see this filamentary structure, bent filament, which you don't see in 13CO at all. In the green here. Now, if you look at it in ammonia, a high density tracer, you can see which is mapped here in the grayscale. You can see it very clearly, and this is with a low resolution observations with the GBT, the Green Bank Telescope. But if you go and map this with the VLA and combine the data with, from the very large array, this is in interferometer, and the GBT, you get a much nicer map that shows very clearly the filamentary structure of that region there, which is not seen at all in the 13CO. And it's not even because partly it's because it's optically thick, the CO, but also what happens to carbon-bearing molecules like CO is that they can all in very dense and cold regions, the CO then starts to stick to the grains and freeze out, and they cease to exist in the gas phase. And so if the CO is not in the gas phase, it cannot emit in the millimeter, so you won't be able to observe it. So with this carbon-bearing molecules, it's hard to see the dense regions, and this is another example of this. This is C17O, another of the isotopologues of CO, that is the CO molecule, but with 17O isotope of the 17 isotope of oxygen, which is in principle should trace dense regions because of its abundance, but you cannot see the filamentary structure here in the map, in the reddish map, not because it's optically thick in this case, but because the CO gets depleted, as we call it, because it freezes into the gas grain, into the dust grains. Something that it doesn't happen to the nitrogen-bearing molecules like ammonia. It's harder for them to stick to the grains when it's cold. So what can you do with ammonia in addition to probing the structure? You can study the column density, and from it we can see that there are different condensations along the filament, and this could be because of fragmentation along the filament. Could this be the form, the start of a star forming core forming there? So, you have the filament. The story goes that you have the filament, and then from the filament you form the core, well, you form condensations and you fragment, and those little fragments then gather up mass to become a core and then to form a star. So it could be that we're seeing the beginnings of that. We can also study the velocity dispersion. That is how much dispersion in the velocity there is of the gas along the line of sight. And the darker colors here are lower velocity dispersion, which means lower turbulence. And we see that in some of the condensations, the lower the velocity dispersion is lower, which it could be that I mean, people have said that that you need so-called coherent cores, that is cores where not only you have dense gas, but you have low turbulence in order for stars to start to form. And also we can study the temperature when using more than one transition of the ammonia. And here's a temperature map, and you can see that it's warmer, it's colder in this condensations, and it's warmer here close to the protostar, the only protostar in this region. Could it be because of feedback from outflows? Most likely it is. Certainly that's what has been seen in this other region. This is the Serpent South molecular cloud. Very nice filamentary structure, solar filament. And in the center of that filamentary structure, which sometimes we call hub, when you have filaments from different directions connecting into a central part, that's usually typically referred to as the hub. And usually in the hub is where we see stellar clusters. And then you can see all the stars that are in that central hub there. So this cloud was observed in ammonia, also with the VLA and the GBT. And again, you can study the velocity dispersion of the gas, which you see that it's lower at the outskirts here and higher in the center. And you can study, you can derive a temperature map, which again, you see that it's lower in the filaments here and higher towards the center where you see the stars. And this is most likely due to outflows in the region. There are many stars there. Here's a blow up. It's a blow up of this region, the central hub, where you see there's many protostars, and there's an increase in the temperature as seen as the white color, and there's also an increase in the velocity dispersion as you see from the contours. And in fact, this increase in the velocity dispersion, it's coincident with a very nice outflow that we see there in the center. And not only do you see an increase in temperature and velocity dispersion of the gas in this region, but we actually detect, well, they detect, I didn't do that, they detect ammonia 3,3 emission, which typically comes with very hot gas. This the upper level of this transition, it's quite high, so you need high temperatures in the hundreds of Kelvin to excite it. So with this dense gas tracer, ammonia, we are able to understand, well, at least study the dense gas in clusters in regions around protostars and see how the feedback affects that gas. So that's with ammonia. Now I'll be, from now on, well, most of the dense gas that I'll show will be from using N2D+. That's another dense gas tracer. And in this case, deuterium, which is the heavy hydrogen, it's it's part of this molecule. deuterated molecules, as we say, those are molecules that instead of having the normal hydrogen have the deuterium isotope, the heavy isotope of hydrogen, are good tracers of cold and dense gas. And here, again, well, this is Orion B, or a part of Orion B. This is a very nice optical near-infrared image of this region, obtained recently with the Euclid Space Telescope, which was recently launched by the European Space Agency. And we're concentrating on this region here, which has a bunch of stars, bunch of protostars there. It's a filamentary structure, which is seen here in continuum emission, again, emission from the dust. The resolution is not great because it's Herschel with a 15 arc-second beam or so. But if we go with ALMA and observe it with ALMA, here's the orange. Here is the dust continuum. Observe with ALMA, and you can see the beam here of the dust continuum from ALMA. It's about 1 to 2 about 2 arc-seconds, much smaller than the Herschel by a factor of 8 or so. And you can start seeing the different structures in the dust. Again, the dust doesn't give you much. It doesn't give you any information on the kinematics, so we need to use a gas tracer in order to study the velocity structure of the gas. And in this case, we'll be using N to D plus, the 3 to 2 transition, which has emits in the 231 gigahertz or so, easily observable with ALMA in band 6. And here is shown in the orange, orange purple map, and the green contours are the dust continuum. So in most cases, not all, but in most cases, the N to D plus traces the dust continuum. And it does, let's see, maybe I can see it here better. It does a better job at the N to D plus does a better job of tracing the dense gas when it's very cold and very embedded. When you have protostars forming, which start to heat up the surrounding, then that heat destroys the deuterated molecules, and you cannot use them anymore to trace the dense gas. So N to D plus is good for tracing starless, cold gas. But there's a lot of region here. There are a lot of regions here that don't have heat, that don't have protostars. It looks like there are starless cores, maybe cores that will eventually form stars. And one interesting region here is this filament that we studied, which we saw that it has a very peculiar velocity gradient. You see that this is here on the right, it's a velocity map. So to the left is the integrated intensity map of the region, just total intensity emission from the N to D plus. And here I'm showing the average velocity per position of the gas in this map of the N to D plus emission. And that filament here looks like it's has a very nice velocity gradient from left to right, perpendicular to the long axis of the filament. And we claim that it's due to rotation. Cores have been found to rotate. The cores, again, are the dense regions that form inside filaments, which then form stars. And it is a current topic on research to understand how is it that the cores inherit their rotation, their angular momentum, which then they give to the protostar system and disk. Is it just because of turbulence motions that form the core, and as because of that they start rotating, or is it because the filament where they form it's also rotating, and that rotation it's then given to, so to speak, to the core. So that's what we were trying to figure out here. In this particular case, this is what we think is the first filament that we see that is rotating like that. We didn't think that from our results that it was that the cores inside that filament were inheriting the angular momentum from the filament. It looks like, at least in this case, the cores and the filament form at the same time and don't have any effect on each other. But this is just one source. Similar studies should be done in order to understand what's happening here. So, but this structure is not the only interesting thing that we saw. So we saw that there was a very nice a velocity structure there, a rotation that we call that it's that we interpret as rotation, but it got kind of messy as you get closer to the continuum sources, which are shown here in contours. The arrows here show the velocity gradient, and the colors are the colors of the arrow indicate the average velocity. And in other regions, and this other parts are not published, we see interesting features in the kinematics. We see that between continuum sources, again the contours show the dust continuum, which could be starless cores or pre-stellar cores. We see that there seem to be gradients pointing towards regions in between the dust continuum, both in this region and in the south. We don't know what it is. We're currently investigating that. Well, actually, no one is, but we saw that, and we need people to understand. We need people to try to take a look at it deeper. Okay, so you can study filaments with n to the plus. Let's go to smaller scales, the core scales. Let's see how we're doing in time. Okay, good. So these are smaller scales. The core scales about 0.05 parsecs to 0.1 parsecs, or if you like AUs, in thousands of AU, astronomical units. And when we were observing our ALMA, we had an ALMA project to study 21 sources at different evolutionary stages. So these are protostars at different evolutionary stages, and among the youngest protostars, the most embedded and obscured and younger protostars, the class 0 sources, we noticed that n to the plus was probing or showing very filamentary structures and around the protostars. So 6 out of the 7 class 0 protostars in that survey showed interesting n to the plus emission, actually showed n to the plus emission, and all of them showed this kind of elongated structure. In this images, I'm showing the position of the protostar with the white contours as probed by the or green contours as probed by the dust continuum emission. The red and the blue contours show the outflow from the protostars, and the orangey, the purple, yellow maps show the n to the plus emission with very filamentary structures. In some cases perpendicular to the outflows, in some they're not. Out of this 6 protostars where we see this n to the where we detect n to the plus, 4 of them showed with their kinematics what we think is consistent with infalling motion. So if we take 3 out of those 4, because we'll concentrate on this 4th source later, And what we think it's happening is that this regions are probing what appears to be infalling streamers. And infall streamers are elongated structures around protostars, filamentary, which, if you take a look at their velocity structure, they appear to show velocity that is consistent with what you would expect from gravitational infall. And what would you expect from gravitational infall is velocity increasing towards the center of the, as you get closer to the protostar, because the protostar and the center is where you have the gravitational well there, and the material, as it's getting closer to that protostar, the velocity of the material will increase, and we can study that by looking at the velocity along the length of the filaments, and that's what we call the position velocity diagrams that I'm showing here. So in the position velocity diagrams, this is velocity on the y-axis and position on the x-axis, and you can see that as you get closer to the protostar, which is here, the velocity increases. Well, the changes. I mean, it decreases. Yeah. This is the gas. The velocity of the gas changes and increases as you get closer to the protostar. So this structure seems to be consistent with what we call streamers. And why is that important? Why is that interesting? For that, let's take a look at this particular example. This is the fourth example that I showed before, but I didn't show it in the previous slide. This is one of the youngest protostars in our sample, HOPS 169. Here's the N to the plus emission, integrated intensity map. And here's the velocity map, where we can see that it's the velocity. If we look at the top, let's say, it's changing. There's a velocity gradient from the top to the bottom to the center. And there's also some rotation, appears to be some rotation. We go back to the integrated intensity map. Then we modeled the velocity structure as that coming from infall streamers, as you would expect from just gravitational infall. And if we both model the structure of the streamer, how it would look like on the plane of the sky, and the velocity, and those are the lines, we could see that both the structure of the emission as well as the velocity, as shown here in the grayscale, is consistent with gravitational infall streamers shown by the line, both in blue and red. If we assume that these in fact are streamers, infall streamers, then we can obtain a mass infall rate, which we estimate to be around 10 to the minus 5 solar masses per year, which is not that it's common to have those kind of infall mass rates. But what's interesting is that this is the infall mass rate from the actual streamers. There's also an infall mass rate that we can obtain from the C18O envelope, as the envelope traced by the C18O, which is around this region, and that kind of infall is axisymmetric. It looks like to be more spherical and symmetric, and so you have two kinds of infall feeding the protostar: the classical axisymmetric infall as traced by the C18O, which we also derive to be around 10 to the minus 5 solar masses per year, and the less classical, I guess, infall streamers, non-axisymmetric infall that appears to be happening also in this particular source. Now, we're not the first one to discover infall streamers, and so the infall streamers have been seen in other sources. But what we're saying is that it's important to take those infall streamers into consideration, because at least in this source, the amount of infall rate in the non-axisymmetric infall is similar to that of the classical infall, and so there's a range of material that is falling in to the gas, to the protostar, and so if we want to understand how the protostar acquires its mass and the whole mass assembling process, we need to take in consideration both the axisymmetric infall as well as that material that is being brought to the protostar by the streamers. So those streamers are important. And so a survey of streamers should be done. Oh, this is what I just said. Okay. So this is, oh no, again, so this is the ALMA data, which is very limited in size. It only has about a few thousand AU in size. I didn't put a scale there. Sorry about that. But if you take a look at the large scale map of the gas surrounding the ALMA data, again, this here is the ALMA field of view. This is the N2D plus from the source that we were seeing, and you can see that the C18O from this large scale map obtained with CARMA and the Novayama telescope traces a structure that appears to be consistent, at least it's elongated, along the same axis as the N2D plus, but at larger scales. So it could be, and then it's no surprise that those streamers could be much larger than the ALMA field of view, because we see the N2D plus extending all the way out to the end of the field of view. So, it's not a surprise to see that those are actually extending further. And if we look at if we zoom out even further, we see this structure. Now, this is very speculative. We haven't done much investigation about it, but could this be another large-scale infall structure? Well, we take a look at the velocity structure of that filament, and we see a very nice velocity gradient, as you would expect if you have infalling material. Now, this is again speculative. We have to look at it in more detail, but it could be that we are seeing large-scale streamers that are about 0.8 to 1 parsec in scale. And why is this important? If it is true, then that means that if you have material, let's say, falling all the way from the end of the filament at 1 kilometer per second, which is not this is an order of magnitude estimate. It would take about 1 million years to go from here to the protostar system. 1 million years or 500,000 years is the 500,000 to 1 million years is this time scale that it takes a protostar to form, to go from protostar all the way to a pre-main sequence star. That's that is the general belief, is that protostars acquire their material over a time scale of 0.1 to 1 million years. Actually, it's usually more 0.5, but yeah, 0.5 to 1 million years. So that means that there's continuous material coming in and falling into the protostar disk system from the beginning of the protostar, from the formation of the protostar all the way till the end of the protostellar stage. And why is that important? Well, that it means that there's fresh material coming in to the system continuously throughout the life of the protostar, which can bring in fresh material to the disk, for example, which can then lead to planet formation throughout different stages of the protostellar life. And just here's another one of the sources, HOPS 164 that we saw before. This is the N2D plus map. This is the ALMA field of view. You can see again that the C18O shows what appears to be an elongated structure along the same line of sight. Oh shit, I'm sorry. I'm taking too long. But anyways, this is the velocity gradient, which, could it be Infall? We don't know, but it's interesting that we take a look at that. Okay, so like I said, part of this I made it longer, but I guess I made it too long, and I took longer than I took in Morelia when I gave when I gave the talk. But the reason I'm concentrating in dense gas, not only because it's important for understanding dense gas, the formation of stars, is that this particular molecules, which trains dense gas, will be very nicely mapped with a telescope that is being planned to be built in the next 10 years. And I say planned because it's still, the money's still not there, but the people are still planning to do that, which is called the NGVLA, or the Next Generation Very Large Array, which will provide 10 times higher resolution and sensitivity compared to other existing and planned telescopes. Here's an artist concession of the core of the NGVLA. The NGVLA will be made of many different antennas. It will be an interferometer of 200 or so antennas. This is just the core because, the NGVLA will be a much better, a more powerful telescope than the VLA, which is shown here, is the Very Large Array in New Mexico, and the VLBA, which is the Very Long Baseline Array. So the NGVLA intends to be a combination of these two and even more powerful. So the VLA is an array in New Mexico. The VLBA, it's also an array, but it's an array over many large distances throughout the continent. And the NGVLA includes many dishes with a wide range of baselines. And here are the different baselines that of different positions of the dishes where there will be. Here's Texas, here's New Mexico, where the core of the array will be. And inside that spiral, there will be more antennas. So in total, there will be about 200 something antennas. And it will be made of the main interferometric array, the red and the blue dishes here, as well as the long baseline arrays, which you see here in purple, which will extend all the way from Hawaii to the continental US and, in principle, Puerto Rico and St. Croix. So it will have much better resolution than existing telescopes like ALMA and the SKA, the Square Kilometer Array. So NGVLA will surpass them in resolution at different wavelengths. Much better resolution than JWST and HST, for example. We're talking about milliarc seconds here. So very small resolution, very high resolution. And the range of frequencies that we'll observe will go from what is planned for the SKA, the Square Kilometer Array, which will be in Australia and Hawaii, and South Africa, as well as the VLA, but it will extend all the way to the lower frequencies of ALMA. So it will go from about 1 gigahertz all the way to 112 gigahertz. And among those different bands, we have the transitions from molecules that are very good at tracing dense gas, like ammonia in the 20 to 25 gigahertz band frequencies in band 4, and N to the plus, but now the 1 to 0 transition at 7.1 gigahertz, and other all other transitions and molecules that are very good at tracing dense gas as well, like the deuterated ammonia and N2H plus. And yeah, so N to the plus 1 to 0 will trace even colder gas than what the N to the plus 3 to 2 transition that you can observe with ALMA. So you can trace colder gas, for example. Now here's a list of, let me just keep this, because this is just a list of other deuterated molecules that can be observed at these frequencies in the band 6 of NGVLA. So not only N to the plus, but other deuterated molecules that can be used for studies of chemistry as well as dense gas observations in star-forming regions. And as a comparison, the ammonia map that I showed before had a beam of around 6 arcsecond, as shown here in this white dot, with a field of view. Each position, each pointing with the VLA had a field of view of 1.9 arc minutes. With the NGVLA, because the antennas are smaller, you have a larger field of view, and since you have many more antennas at longer baselines, you can have a smaller beam, and so you can map the ammonia on this region. For example, this region here where I show the presumed large-scale infall structure, you can map this in ammonia relatively easily with, I don't know, 10 pointings or so. And have a very high resolution as well. Let's see. Should I? Well, let me. One last thing that I mentioned there in the last 10 minutes that I have here, in the conference in Morelia, was this the decadal survey. The astronomy and astrophysics community in the U.S. has a decadal survey every 10 years, hence the decadal survey, where people talk about the research that should be done, or not should be done, but it's the most interesting research that will likely be done in the next 10 years, and the instruments that should be built in order to conduct that exciting research over the next 10 years. And that's how the NGVLA, actually the NGVLA was chosen as one of the telescopes, observatories that should be funded in order to carry out the interesting research that it will carry out. And NGVLA will carry out, if it's ever built, will carry out many different other research topics than what I showed here. So if you have questions about that, let me know. But among the different chapters in the decadal survey, in addition to the research and the instruments that should be built, there was a chapter on the profession and its societal impacts. And it talked about sustainability and the impact on the environment and diversity in the field. And one of the recommendations that came out of that in that chapter was the astronomy community should work with experts from other experienced disciplines, as is archaeology, for example, and they gave that as an example, and representatives from local communities to define what they call a community astronomy model of engagement that advances scientific research while respecting, empowering, and benefiting local communities. And they gave it as an example, archaeology, which has been doing this for a while. Archaeology and other social sciences have, in their beginnings, a very colonial attitude, but they have learned from those mistakes, at least some of the people that carry out that kind of research, and they have come up with what they call community-based social sciences or archaeology. And in particular for astronomy, that should include some of the following principles, as mentioned in the Cato survey: listen and empower, aim to do good for all, and invest in the future together. That is, in particular, make an effort to work in partnership with communities and stakeholders to create a future defined by positive, long-lasting mutual benefit and respect for diverse ways of knowing. And the reason I gave this um, slide there is that, if you notice that one of the antennas will be placed in Puerto Rico. Specifically, they mentioned that it's in the Arecibo site, right there. And currently, there are people working in Puerto Rico, astronomers and engineers, working to put together this 12-meter, to resuscitate this 12-meter telescope at the Arecibo site. So by the time that if they ever decide to build NGVLA and put the long baseline dishes there, there will be, and there's already astronomers and engineers experienced in radio astronomy, but there will even be more if we actually make this happen with the 12-meter. There will be people ready to interact and collaborate with the people in the NGVLA and to put those antennas to good use. And the reason I say that is because it should not be as it's done in the past, where, for example, in St. Croix, where one of the VLBA antennas are, they just put the antenna there, put a cyclone fence around it, and have an operator use it, take care of the antenna every now and then, and not involve the community. Or they could do, sometimes what they say, what they're doing for the community is just having little here one outreach activity here and one outreach activity there, and they call it a day. So it shouldn't be that way. It should be as a community based astronomy principles. It should be a conversation with the community there to see what they want, how they want, how both how the stakeholders will benefit, and how both the project and the local community will benefit from the project. So maybe some communities only what they want is a few outreach programs. Well, so be it. But if some other communities want to be involved in the project, then that should be the case. So the NGVLA has a let's see if I know. The NGVLA has a good opportunity to start to do that community-based astronomy, given that they have telescopes all over the US and in Mexico, and they will have to deal with different communities. So they could set a good example, if they do it right, on how to do community astronomy. And with that, I'll leave it there. Thank you.